Hello, and welcome to another section about equilibrium reactions. We're going to talk today about something called Chatellier's Principle. Basically, it tells us what happens when a change is imposed on a system at equilibrium, and that's all we're going to talk about. We're going to look at what kind of changes could be imposed. We could change the concentration of different reactants or products. We could change the pressure or volume. We could change the temperature. Here, just representing a system at equilibrium, we have reactants, we have products. We have the rate of the forward reaction equal to the rate of the reverse reaction. What happens if we add a bunch more reactants, change the concentration of something? What happens to our equilibrium? What happens if we change these other parameters? Basically, Le Chatelier's principle states that the position of the equilibrium, when a change is imposed, will shift in a direction that tends to reduce the effect of that change. So if we add more reactants, this equilibrium is going to shift to the right to bring us back to our level seesaw. So let's look at the specific things that we can change in a reaction at equilibrium. Let's start with concentration. So let's look at changing the concentration within a reaction. Here's a reaction, the synthesis of ammonia, and it is at equilibrium. We have the rate of the forward reaction equal to the rate of the reverse reaction. What happens to this if we add more hydrogen gas? Well, if we add more hydrogen gas into this system, we increase the concentration of the hydrogen, and the reaction will shift to the right. That is in order to make up for that change that we imposed on this system. We can see that over here in this graph. If we have we have our hydrogen, we have our nitrogen gas, right here. We have our product, ammonia. They're at equilibrium. They're obviously in different concentrations. Equilibrium doesn't mean everything's in the same concentration. Remember, it just means it's the same forward rate and reverse rate of reaction. And that they are stabilized, their amounts are stabilized. If we add more hydrogen at this point right here, we put more hydrogen into the system, it is going to shift our equilibrium to the right. This happens as the reaction, in essence, tries to balance itself out so that the forward rate and the reverse rate will be equal again. And we can see that happening on this graph, where right here, they're once again in equilibrium. Now, let's look at adding more nitrogen. What would happen to the reaction if we add more nitrogen? I'm going to increase the concentration of the nitrogen here. So the equilibrium is going to, again, shift to the right because we have excess nitrogen being added, and the equilibrium will shift this direction until it is able to stabilize, and the forward and the reverse rates are once again equal to each other. What if we add, we've been talking here about adding more, increasing the concentration of the reactants. What if we increase concentration of the product, as in this case right here? What if we add more ammonia? What happens then? In this case, we have more ammonia, so the equilibrium will shift to the left. It's going to drive the reaction this direction, the reverse, rather than the forward, until we get equilibrium reestablished. So now let's look at changing volume. And when we change volume, we affect the pressure as well when we're talking about gases. So let's look at, let's look at this system right here. You know that if we have a larger volume, here's our, say, volume, given some volume. If we have a larger volume, we're going to have lower pressure in this system. Obviously, if we decrease the volume and have a lower volume, we're going to increase the pressure on this system, aren't we? I mean, you can think about that. They're always inversely, these two are inversely proportional to one another. When we have larger volume, we have fewer collisions per unit area. and a lower pressure. When we have a smaller volume, we have more collisions per unit area and a higher pressure. So how will reducing the volume affect this given reaction? When we're talking about volume and pressure, the equilibrium is going to shift in order to reduce the pressure. That's just what happens when we're talking about volume and pressure. So let's look at what this means for the direction that the equilibrium will shift. In a gaseous reaction at equilibrium, when the volume is decreased, the system shifts in the direction that gives the smaller number of gas molecules. So let's look at this example. We have calcium carbonate as a solid. We have calcium oxide as a solid product. We also have carbon dioxide gas as a product. Well, if we were to decrease the volume in this system, the equilibrium is going to shift left. Why? Because there are fewer gas molecules to the left. Here we have no gas molecules, it's just a solid. Over on this side of the equation, we have one molecule of a gaseous product. So one molecule of gas on the right as a product, none on the left, so the equilibrium shifts left in this system. Let's look at a different example. What about this one? What would happen if we decrease the volume? This is a system in equilibrium. We're going to decrease the volume. What direction is this equilibrium going to shift? Well, in this case, this equilibrium is going to shift. We're decreasing the volume. So as we decrease the volume, the equilibrium shifts in the direction that gives the smaller number of gas molecules because it wants to reduce the amount of pressure. So the smaller number of gas molecules would be over that direction. It shifts to the right. There is one molecule of gas here, or excuse me, two, right? 2 molecules of gas over on that side of the equation, 4 molecules of gas on the left, so the equilibrium shifts to the right toward the products. What if, instead of decreasing the volume, what if we increase the volume in a system? What if we have a closed system at equilibrium here and we allow it more volume? What is going to happen in that case? Increasing the volume will shift the equilibrium to increase the pressure. So, in a gaseous reaction, at equilibrium, when volume is increased, the system shifts in the direction that gives the larger number of gas molecules. So, in this case, the larger number of gas molecules, remember we have 4 on this side, 2 on this side, so in this case, the equilibrium is going to shift left because it's going to go toward the larger number of gas molecules. Now, here's something to note, an important note for us here. Changes in concentration, we've just talked about, volume and pressure, we've just talked about, they alter the equilibrium position, but they do not alter the equilibrium constant. Remember when we talked about the equilibrium constant, K, and calculated values for that. At any given temperature, the equilibrium constant always remains constant at any given temperature. So far, when we have made changes to our equilibrium system, what we've just talked about, concentration, volume, pressure, we've not changed the temperature, our equilibrium constant will still be the same for those systems, but the equilibrium position, the individual equilibrium position will alter and adjust to compensate, to maintain that equilibrium constant. We're now going to talk about temperature. Temperature does affect the equilibrium constant, so that is something important to keep in mind. One other quick note, when we are talking about volume and pressure, notice that we're talking about a gaseous system, we're talking about gases. If liquids and solids are involved, remember those do not affect the volume and pressure because they have a stable, constant volume and you can't change their volume, but you can change the volume of a gas. So that was just another little side note for you. Next, we're going to talk about changes in temperature. What happens when we change the temperature in a reaction? First, let's just review. You guys, I'm sure, remember the difference between an exothermic and an endothermic reaction. An exothermic reaction produces heat. Heat is a product. An endothermic reaction uses heat. It uses energy. Heat is, in essence, a reactant. Okay, so if we have here are two examples. Here's a reaction that is exothermic. And I wrote that right there. It's an exothermic reaction. So when it's exothermic, we know that energy is released. It tells you exactly how much energy is released. Because energy is released, I write that as a reactant on the right side of the equation. You can do that. It's part of what is given off. Energy is released. It's exothermic. What about an endothermic reaction? Right here we have an example of an endothermic reaction. Energy is needed for this reaction. So it tells us exactly how much energy is needed. 556 kilojoules of energy is needed for this reaction. So in this case, we write that as a reactant on the left side of the equation because it needs that energy. It's going to use it. It's endothermic. So the first step in looking at what happens in an equilibrium reaction when you change the temperature, first look, is the reaction exothermic or endothermic? Then when you write the reaction, include the energy as either a product or reactant, just like we did right here. Then we can predict the direction of the shift. So how do we predict the direction of the shift? It's just like we did for concentration. If we have in this exothermic reaction, if we add heat, we're adding more of this, which means we're going to shift the reaction this way, to the left. If we look at an endothermic reaction right here, and we add heat, we're adding more heat, which in this case is a reactant. So that means we're going to shift the reaction this way. What if we cool it down? Cooling the reaction was going to give us the opposite effect. So let's look at our first problem right here. We have our exothermic reaction. If we are going to cool it and put this basically take energy away by cooling it down, it's going to have the opposite effect. Instead of going to the left, the reaction will shift to the right, not to the left, right? If we cool it down. And on the bottom, for our endothermic reaction, if we cool that down, it will do the opposite. It will shift to the left because we're taking energy away. We're removing some of this. So it will shift the reaction to the left. So, quick review. Le Chatelier's principle just states that when a change is imposed on a system at equilibrium, the equilibrium will shift to counter that change. Remember it right here is just sort of a little example. We have a system at equilibrium, the initial equilibrium conditions, the initial equilibrium positions, right? We do something that makes a change. We either shift to the left or here it's shifting to the left again, begins to shift to the right a little more until it finally reaches equilibrium, and we have an equilibrium position that returns. It's an equilibrium state that returns. It's not the same equilibrium position as this one, but it is equilibrium because the forward rate is equal to the reverse rate. So hopefully that was helpful, and make sure you do the worksheet on these and practice how temperature and concentration and volume and pressure affect the equilibrium systems. If you want some advanced ideas, there is an advanced proficiency problem on that worksheet you are welcome to try and tackle, and I look forward to seeing you in class.